I do know that your lab will you'll have an hour and 15 minutes in each lab. We're going to do them in 2 groups. I haven't told my lab yet who's coming first. I'll have to figure that out. Whoever comes first for the midterm will come second for the final. So I'll try to keep it, fair for y'all so that you don't have to come early both times. And that's true for the other labs too, that you'll come at different times. I'm just going to go through the midterm study guide. I sent it out to you on the Moodle page. It looks like this. And basically everything is that's on the midterm study guide is going to be on the midterm. I brought the exam, it's right here, and I'm going to go through the questions that are on the exam. Not exactly, but you're going to calculate standard error. You have to do a projectile motion problem. So I'm going to go through each of those and show you the different types of problems that you'll see. Is that cool? Remember, no multiple choice. So I know I've said in the past that, hey, you want to keep those quizzes and study them. But since we have a limited time, I decided to do just free response. And I and Dr. Verma and Dr. Young, we all get partial credit. So the really easy exams to grade are the ones that are perfectly right. And a lot of you will get them perfectly right. And so, and the other really easy ones to grade are the ones that don't have anything at all. So don't be that person. Like, even if you write something that's true about the problem, then you'll get some credit for it. Okay? Don't leave any question blank. Okay, so the first is from lab number 1, and there'll be 2 things that you'll see from lab number 1. The first is calculating standard error and/or standard percent error. So standard error, what I'm going to do is I'm going to give you a set of values. Let's say I'll give you a 3, 6, 7, what's that, 9 plus 16, 8. So I'd give you those 4 values, and I'd say, what is the standard error of these values? There are a couple of steps that you have to take. You don't need to memorize the equations. I'll give you the equation for standard error, but you do need to know how to calculate mean. I think you all know how to calculate the average of a set of values. So first, I would calculate the average, and that's going to be, what's that, 9 plus 15, 3 plus 6 plus 7 plus 8, divided by 4. That's the number of values in the set. 9 plus 15 is 24. Divided by 4, that's equal to 6. That would be your first step, is to calculate the average. And then to calculate the standard error is the square root of x minus x bar squared divided by n times n minus 1. Don't memorize that equation. We'll give it to you. It'll be on your test for everybody, for all of your exams. I mean, for all the classes. And so what's that? The x minus x bar is each individual value minus the average value. So I'd say 3 minus 6 squared plus, there should be a summation here, by the way, 3 minus 6 squared plus 6 minus 6 squared plus 7 minus 6 squared plus 8 minus 6 squared. And then I divide that through by n, which is 4 times 4 minus 1. And so that's going to be the square root of 9 plus 0 plus 1 plus 4 divided by 12. 4 times 3. So that's the square root of 14 divided by 12. The other exams that are really easy to grade are the people that just write down a number that's wrong, or even people that write down a number that's right. I really want to see your work, okay? I'm not going to give you full credit if you don't show your work. And so I get a value of 1.1. And so if I were to represent the value for x, I would say that x is equal to 6 plus or minus 1.1. Or really, to keep my sig figs correct, I would say 6 plus or minus 1. That is how I would represent that value. That problem is on the exam. I give you 4 numbers and I ask you to calculate the standard error. Problem number 1. Yeah.
Pick up points for sig figs.
Yeah. Especially on something like this, where sig figs were part of that lab experiment. Now, on some of the later problems, if you had 2 or you should have 1 sig fig, I'm not going to count that off. But on this problem, yeah, I'd count off for sig figs. In my problem that I give my students, there are 2 sig figs in every data, so you'll need 2 sig figs in the final answer. Okay. The next thing that I'll do, and I didn't bring a caliper. Let's see, do I have a caliper tutorial? I think we do, right? But you're going to have to use a caliper. And so review how to use a caliper. Let's see, we had one that was good and one that wasn't so good. I don't like this one. The other one, Caliper Simulator 2. I don't like this one either. I'll bring a caliper if y'all want to practice with it. But what I'm going to do is I'm going to give you a cylinder, and then you have to figure out what is the diameter of that cylinder using a caliper. Okay? After we're done here, I can go upstairs and get it to you, and we can review that if you want. The caliper, remember, measures in centimeters. And with a caliper, I'll be looking that you have the proper number of decimal places. And so you should have, do y'all remember how many decimal places with a caliper? No, not 2. It would have 3 decimal places. And this last decimal place, isn't that right? Yeah, 3 decimal places. This last decimal place is either a 0 or a 5. Let's see, let's look. These simulators are not very good, but let's look at the old exams. I think I have a multiple choice question on those. These are useful to look at. They'll give you a good feel for what the midterm is going to be like. I mean, this one's almost identical to the midterm that you'll have. All of these are. Oh, here we go. This is a great one. This is what our calipers look like. So remember, with the caliper, the first thing that you do is you look at this point right here. A common error that people make is that they look here. That's not what you do. You look at where the 0 lines up with a tick mark on the top. So not right here. You look right here. And notice that that lines up just before sorry, I'm getting rid of the line. Okay, so that lines up just before the 0.9. So it's somewhere between 0.8 and 0.9. So that's going to be my first decimal point, is 0.8. At that point, for this multiple choice, yours isn't going to be multiple choice, but I could say that the answer is going to be right there. Next is I look along the bottom scale, looking left to right, until I find a point that lines up with the tick mark on the top. So I see right here that it lines up with the tick mark on the top. Notice that all these others, those don't line up, those don't line up. They don't line up until you get to the 8. So that is our second decimal place. And then the third decimal place comes from, does it line up with this point or does it line up with this point? If it lines up with the first one, that's a 0. If it lines up with the second one, that is a 5. So this will be 0 and this will be 5. This last digit, like if this was your reading for the diameter, then I would say that I would accept anywhere from like 0.870 to 0.895. There's going to be a range. You're all going to have a very similar cylinder, but depending on where you measure the diameter, it might be off by 1,000 or a few thousandths of a centimeter. Okay? So be prepared for that. We can go up and get a caliper if you don't want to put your hands on one, but you can also follow this example as well. All right, that's the second question that's on the exam. The third question that's on the exam is on every exam that we've ever given. I'm sorry. Oh, goodness. Don't capture the ink. Clear the ink. The third question is going to look like this. All right, the relationship will be different. We've done several like this. This was the lab where we had the t equals 2 pi over root g root L. And remember, I gave you values for L and t, and you had to figure out what is the acceleration due to gravity. In this case, you plotted t on the y-axis and square root of L on the x-axis, because this is following the equation of a line. And then this coefficient to the square root of L is the slope of that graph. You're going to have to do something similar. For example, on this problem, where I give you the function, which is v squared equal 2ax, what you're going to plot is going to be v squared, that is your dependent variable, versus delta x. So you have to create another column here where you calculate v squared and then plot it versus delta x. I'm going to give you a sheet of graph paper, and I'll expect to see the plot on the graph paper. You draw a best fit line, you find the slope of that best fit line, and then your slope is equal to, in this case, it's going to be equal to the coefficient, which is 2a, and you solve for that acceleration, slope divided by 2. But don't expect it to be that function. Expect it to be really any function. I could just make up a function. Or it might be our kinematics, one of our kinematics equations, the x equal 1/2 at squared. We did that in class. You might have an example of that in your lab manual. I think you do. It'll look a lot like this. Same layout, just a different function and different data. That's problem number 3. On this, make sure, one, that you use your graph paper for this plot, that you label the axes clearly. So this would be meters squared per second squared. This will be meters. I'll put my units on there. Make sure that the scale takes up most of the page. So there'll be some practice in sort of figuring out what the scale is to get those data to span across most of the page. It doesn't have to fit perfectly on the page, but 2/3 or more of the page the data should span. When you find your slope, remember, I don't like it when you use data points, but you really need to pick points that are not on the line. So I pick a point here and here. I don't find my slope like that. That's not good, because that means that you're really only using 2 of your data points and not all of your data. Okay? That question is worth 15 points. It's question number 3, and it's 15 out of 65 points. So it's almost a quarter of your exam grade. The other questions, by the way, are 5 points each. The standard error and the caliper are only 5 points each. All right, let's look at our graphing. I am not, in my class, I'm not going to expect you to do the pendulum. You might have to plot it, but I'm not going to ask you to actually do it as a practical. The only practical that you'll have in my lab is the caliper. Okay? The next topic is video analysis of motion. On that, we had several things that we did in lab. This was the one where you had the basketball, the bouncing basketball. You're going to need to be able to describe the motion for each of those, 3 scenarios. You had one where you just dropped it. I want you to be able to draw y versus t and x versus t. Well, not x versus t because it's 0, but y versus t and vy versus t. Y versus t, let's see, it starts out with what's it look like this, right? The y versus t starts out with a small velocity and then increases in the negative direction. And then the vy versus t is going to look like this. Be able to draw those graphs for all 3 scenarios. Let me draw the others. I also want you to point out here that the slope of this graph is equal to -10 meters per second squared, because that's the slope, the acceleration due to gravity. The second situation that we had was where we threw a ball like that to your friend, and then my y versus t looks like this, and then my vy versus t Let's see, it starts out with a big positive velocity, like this. It goes to a 0 velocity, and then it continues on in the negative direction. So my Vy versus t will look like that. I'm going to expect you to draw these. So I'll describe the situation to you. You're dropping a ball, you're passing a ball to your friend, or the third one is that you bounce a ball. And the bounce ball, physically, it looked like this, the bounce pass, and the y versus t. See, what did the y versus t? Well, it starts out with a small positive velocity. It increases. It looks a lot like the path, actually. The y versus t looks like that. And then the Vy versus t looks like this. Small negative velocity that gets bigger in the negative direction, and then it jumps to a really big positive velocity, and then that drops back down towards 0 as it reaches your friend's hand. Also, the x graphs are simpler here, but be able to draw those as well. Let's go back and do those. So if I do x versus t, this one looks like this. I'm not sure if y'all remember in that lab that it actually slowed down. At this point, this is the bounce. The Vx versus t should look like this. Start out big and end up small. That it has a bigger x velocity before the bounce, and then it has a smaller x velocity after the bounce, but still constant. Let's go back and do those for the previous one too. On this one, x versus t looks like this, and Vx versus t looks like that, with a constant x velocity. But I'll tell you, I'll probably ask you about the y velocity, but your faculty might also ask about the x. Emily? Sure. I know this is fast, but if you have any questions, just stop me. I did the exam this morning. It took me about 12 minutes, but I wrote the thing, right? And so it's a lot faster for me to do it, but I think that you'll be able to finish it in an hour with a little difficulty if you really have any idea of what's going on. Don't stress the exam. The exam seems like a big deal, like we call it a midterm exam, but it's only worth 65 points. And so if you bomb the exam, it could pull your grade down a letter grade, but it's rare for the midterm to hurt you. Usually the midterm helps you. All right. Can I go from here? The next one has to do with centripetal motion. And Dr. Verma, my wife and I, we talked about it. Oh, no, I'm sorry. Let's do vectors. We'll do vectors first. Yeah, vectors. So I'm going to give you 2 vectors, one off axis, and you have to find the sum of them. This was just like from the exam, right? We had to do this on the exam. Let's just do a quick example. Let's say that vector A is, I don't know, 3 meters at 30 degrees from the x. And vector B is 4 meters in the positive x direction, or in the negative x direction. So I always like to draw the vectors. It really helps to keep me clear on what I'm doing. So I'm going to draw the first vector, 3 meters at 30 degrees from the x-axis. It looks like that. This is 30 degrees. This is 3 meters. And then I have 4 meters in the negative x direction. So those are my 2 vectors. Draw the vectors, resolve the vectors, add x and y components, and then find the magnitude and direction. Those are the 4 steps that we did with vectors. That was true for chapter 4 too, when we did the inclined plane with applying Newton's second law. So I'm going to go and resolve the vectors into their x and y components. This is 4 meters. The x component is 2.6 meters. And then the y component is 1.5 meters. That's doing 3 sine of 30. and 3 cosine of 30. Finding those x and y components. Now, I add x and y components. This was step 1. This was step 2. Step 3 is I add my x and y components. So I have 1.5 right here. And then I have 1.4 right here. That's step number 3. And then step number 4 is finding the resultant and magnitude. To find the resultant, or the magnitude of that resultant vector, I say the square root of 1.5 squared plus 1.4 squared. And I get 2.1. And then to find the angle, I say the inverse tan of the y over the x, opposite over adjacent. That's 1.5 over 1.4. It's going to be really close to 45. 47 degrees. And then I need to declare which axis that is from. That's 47 degrees from the negative x-axis. So that would be the answer. 2.1 meters at 47 degrees from the negative x-axis. We should be really good at this by now, because we've done vectors a lot. So hopefully this is sort of the last chance I get to get vectors out of you before the end of the semester, except for the final, of course, because final email test. Whoop, whoop, whoop. That's good, right? All right. So I want this to be old hand. We're going to do it again next semester. All right. After vectors, projectile motion, you should be able to describe projectile motion. That is, we had this on our exam recently. Dr. Verma, have y'all done it? Projectile motion, had an exam on that yet? Yeah. Okay, so remember what the velocity vectors do. That the velocity in the y direction starts out big, gets smaller, goes to 0, gets bigger in the negative direction. That the acceleration in the y direction is -10, the acceleration in the x direction is 0, and the x velocity starts out whatever it is and then continues on with that motion. Same amount of time to go up as down. The amount of time that's in the air is set by the y velocity, by the y component of that velocity. Just be able to describe what is projectile motion and how it responds, how objects in projectile motion respond. But you're also going to have a calculation. And it's going to be like one of our scenarios that we had in the lab, except we're not going to have to use the quadratic. And everybody's agreed, like me and my wife, Dr. Verma, we all agree that you're not going to have to use the quadratic formula. That means that that problem where you had it set up on the blocks, not going to do that. But really then what that leaves for you is a problem like parts 1 or 4 from the lab, or both. That was the one where you're shooting a ball from a horizontal, and it follows a path that looks like that. And let's say, for example, this distance is 1 meter, then a good question that I might ask is, what is this distance? What is x? The steps in this is that you'd have to find first the time, and what sets the time, the x or the y motion? The y motion. So I'm going to have to use this value for y somehow to find the time. I would say y equals v naught y t plus 1/2 ayt squared. This problem is made a lot easier because v naught y is 0, so that term goes away. And then I can solve this for t because I know everything else. This is -1, half of -10 is -5, and that's t squared. So t then is the square root of 0.2, which is 0.45 seconds. So that's the time. And then if I want to know what is the x value, well, a couple of different things I could do here. I could tell you what is Vx. I could tell you that Vx is, I don't know, 3 meters per second. And if I wanted to know x, then I could say that x is equal to Vx times t, which is 3 times 0.45, which is what, 1.4 meters? So I could do that, or I could tell you what is x, let's say it's 1.35 meters, and then ask you what is Vx. And it'd be the similar problem. You just say Vx is equal to x divided by t. So that would be 1.35 divided by 0.45, which is equal to 3 meters per second. Either one of those. Also, with projectile motion, likely even, is that I'll ask you, what if you put a ring out at x equal 1 meter, just like you did in lab, what is the y position of that ring? And to do that, if you recall from that lab, we said, well, at x equal 1 meter, let's assume that v is 3 meters per second. The t is equal to, let's see, v is x over t. So t is v divided by, no, that's not right. X divided by v. Isn't that right? Meters over meters per second. Yeah. So t is x over v, which is going to be 1.35 meters over 3 meters per second. No, I'm sorry. Sorry. 1 meter divided by 3 meters per second, or 0.3 seconds. So the time that it takes to go from here out to here is 0.3 seconds. And we use our x motion to find that out. And then you have to say, well, y is equal to 1/2 ayt squared to find what is the y displacement. That's going to be -5 times 0.3 squared. Which is -0.45. Okay? Which means it's how far from the floor. If it drops 45 centimeters, how far is it from the floor? 55. So I would say 1 meter minus 0.45 meters is equal to 0.55 meters. You're going to see this problem in my exam. You'll probably see something really similar on your other exams. Okay? Just like in the lab. Just like part number 1 and part number 4 in the lab. And a lot like what we did in the exam, too. All right, what's next here? After that, projectile motion, centripetal motion. So if you look back at the old exams, your centripetal motion is going to be quite a bit simpler for me. That might not be true for your other labs, but I'm pretty sure they're leaning in that direction. We haven't done centripetal motion. Y'all done centripetal motion yet? mv squared over r? No? Okay. You've done it in lab. Have you done it? You're in my class. We haven't done centripetal motion. Yeah. So since we haven't done it in class, we're going to sort of keep it simple for the lab, or I will. What I'm going to require you to do is to interpret this graph. If I give you a graph of position versus time, it looks like this. This is for an object that's going in simple harmonic motion or periodic motion as it goes around and repeats. What I want you to be able to do is to find the period from such a graph and the amplitude. To find the period, you find this distance. So for example, if this is 0.5 seconds and this is 2 seconds, then the period in this case would be 2 minus 0.5, or 1.5 seconds. That's to find what is the period for one full oscillation of that object that's in periodic motion. The other thing I want you to do is be able to find the amplitude. The amplitude is the distance from here to here. A couple ways you can do this. In the lab, you had to find it from here to here and divide by 2 because the origin was offset, was not at 0. But on the exam, you'll have it set at 0. So like if this is 0 and this is 3.2, then your amplitude is 3.2 meters. I don't know what Dr. Young and Dr. Verma are going to do for your lab, so you might want to ask them, hey, to what extent do we need to know how to do the vector diagrams and calculate the period and the tension and all that? In the past, we've done that in more detail, but I'm going to sort of stand back and we'll cover it in class. Okay, so that's all for centripetal motion, even though there is sort of more stuff on the study guide. Really, I'm just doing part B, not part A, and I think that's true for the other labs. Okay, so in number 7, I'm going to give you a graph or a diagram that looks like this. It'll be just like our setup from lab. And I'll ask you to draw the vectors, the vector diagram for this with resolved vectors. And so you could do this on the diagram if you want, or you can make a separate. I'll do both. I'm going to draw my normal force right here. This is Fn. By the way, this angle is 30 degrees, we'll say. I will tell you that this is moving in a velocity up the inclined plane. So I have a force that's pulling it up the inclined plane. Do you remember what we called this? No, never mind. We call it F up or FU, which I know is unfortunate, but that's just what it's called. All right, so FU. And then we also have a frictional force, which is opposite the direction of motion. And then we have the weight. I'm going to go ahead and resolve it into its components. You should know how to do this. If you don't, come see me. The y component is Fw sine of 60. And then the x component is Fw cosine of 60. Dr. Verma might do this differently. I don't know. You might have Fw sine of 30 and Fw cosine of 30 here. I'm not sure how y'all did it in class, but this is correct. And the other way is correct too, but this is just the way I do it. So you could draw it like that, or you could draw another vector diagram just off to the side that's rotated. Either one I would take. Then I'll ask you a number of things. Like I might ask you, hey, what is the normal force? Or what is Fu? Or what is, the x component of blah, blah, blah. So I'll ask you some various questions about that. And then I'm also going to ask you, what is the change in potential energy for this cart if it moves a distance, let's say, like we did in the lab, what do we do, 20 centimeters? If it moves a distance of 0.2 meters, what is the change in potential energy for that cart? Well, the change in potential energy is equal to mg delta y. And so you need to find out what is delta y. Delta y is equal to s times the sine of 30. Let me show you what I did there. I'm going to have this little triangle right here. This is delta y. This is s, which is 0.2 meters. And this is 30 degrees. And so I'm really just doing a little trig skills there to find out what is delta y. And so you would do that to figure out what is the change in potential energy. I would also tell you, oh, by the way, Fu. I would give you the mass that's here, and Fu would just be mu times g, just like we did in lab. That was like number 2 in that lab. I'd also want you to show me how you calculate the work done by that force. And the work done by that force is equal to Fu times s. So it is whatever you found it to be right here times 0.2 meters. And it better be that this work is equal to the change in potential energy. Oh, actually, never mind. Let me see. Never mind. Take that back. Fu is not necessarily equal to this work. It's not necessarily equal to that because our frictional forces is actually taken away. But we're not going to get into all that. Okay? I know I told you the midterm's easy. Like as I spell it all out, it seems not that easy to me. Does it seem easy to you? It's a lot of stuff that we've done, but it might take a little bit of work for you to just remember how to do all that. Is that going to take some work to prepare? And don't stress over it too much. Spend an hour or two preparing, and then move on to your organic exam, which is also on Monday, right? Is that on Monday? That's more important than this lab midterm. More important. Tell Dr. Kalani I said that. Tell him that his class is more important than my class. Okay? All right, questions, concerns? Yeah, Emily? Yeah. Uh-huh.
So, like, could they come early?
Or whoever. Somebody's going to come early, and then somebody's going to come later. And as I said, just to keep it fair, I'll switch it up for the final, because we'll have the same situation for the final. Keep in mind, and if you're working through the old exams, and there's some on that website, that those exams, some students are, 2 or 3 hours through those exams, but we'll make it shorter. I have 8 questions on my exam. These that I've worked right here. So you'll see all of these questions on my exam. Almost identical to this, just the numbers are different. No surprises. Surprises? Don't like surprises. Okay? Other questions? I'm still here if we need some more time. Or we can do one-on-one. Oh, yeah. Let me stop this and dismiss folks. Is that okay? And then I'll run upstairs and we get some. Other people want to see the caliper? Okay. Yeah. Just hang around. Let me pause, stop this.